So today is the last part of the chapter 7 because for 7.6 we still got a similar shape for this topic. So actually if you have recall the memories about 7.3, which is something about the frustum. Okay, so we have using knowledge. Okay, if you have recall the memory, you have did it before. If you got a frustum, okay, you may sometimes using the concept for similar figures. Okay, therefore we have a similar shape here and then told you how to find out the similar products by using a more simple way. So the first thing we learn is the figures for about the area first. So you can see if we get a similar figures, for example a similar triangles, then we have learned it quite a bit long time before. For example, we got a similar triangle for ABC and DEF. They are similar figures. Okay. Okay, and then their length will be in the same ratio for each corresponding length. For example, if this is 1 to 2 in the ratio, that means if AB is 2, then DE is 4. If BC is 3, then EF is 6 because they are similar, right? Because triangle ABC is similar to triangle DEF. Therefore, what will you see is that for the area of this triangle, base times height divided by 2, it should be 3 cm square, right? And then for this is base times height divided by 2, it should be 24 divided by 2, so 12 cm square. Okay, so what will we see? Because if the area is the length base times height, right? So we multiply the side for 2 times. So if this is have a double into this length 4. If this is a double to this length. So for the area, actually we have multiplied the ratio for 2 times. Therefore, we have a formula like this. The area, the ratio of the area is actually to the 2 times of the length ratio. Okay, so we got examples here. If we see this is 2 similar rectangle, what is the area for this? This is the width times length, right? But if we have similar figures for the bigger one, the length should be multiplied by k because the ratio is k. B is also a ratio of k. So therefore you can see if we compare their area ratio, it should be double for the k. So it should be k squared for the area ratio. Therefore you will see the length we just have the ratio of k. But for the area we have a square of k because for the area we multiply the length for both times, so we have a double of the ratio. So therefore no matter you can observe this kind of similar triangle or the similar circle, something like this, or we all did the same thing. If we need to calculate the area, we have to square of the ratio of the length. Therefore we got this conclusion. The area ratio is the length ratio with a square. Okay, and then this is the similar figures case. Okay, therefore we can see if we have example something like this, we just do the same thing because we know that A1 over A2 is equals to the L1 over L2 with a square. Therefore we just putting the corresponding number inside, then we are okay because the area of a smaller circle is 18 cm square and the ratio of their length is 5 over 3. Therefore assume that A1 is the larger circle area. So A1 I don't know, I need to calculate, but the smaller area is 18. And then we have 5/3 with a square for the right hand side. Therefore, you will see it becomes 25/9, and this is 18. We just need to put the 18 to the right hand side, and then the A1 should be 25/9 times 18. Therefore, the area is 50 cm square. Okay, therefore, actually, we know how this relationship is come from, and then we just directly apply this. Then we will calculate the answer for all kind of similar cases. So you can see, for example, 7.22, we even don't have that kind of figures. We just told you that this is two similar figure. You don't even know what is this figure like. Maybe this is a square, maybe this is a triangle, maybe this is a circle. We don't need to know actually what this kind of figure is. We just need to know they are similar figures. Then it's okay. And then the second things, for the length ratio, we always consider this. This should be the side of the figures. And actually, we don't care about this. If this is a parameter, it's also okay. So we just need to compare the same stuff. Is okay. Sine compared to sine. Parameter compared to parameter. Then this is the case we're doing this. Okay, so we again using the formula that we have learned directly. So because we know that the larger figure is 36, and then we need to find a smaller parameter. So this time we let A1 be the smaller one, be the smaller area, and then actually L1 will be the smaller parameter. Okay, this is a corresponding case. So A1 to A2, and then we just put all the numbers inside. So L1 we don't know, we need to calculate, but 36 is something that we can put. And then for the smaller is putting upward, so 98/162. Okay, so you will see the equation is exactly like this. And then because we need to cancel the square, so we make a square root here. If we make a square root and then we multiply 36 to another side, we got 28. Okay. We just need to apply the formula directly. If we see that this is a similar figure, we don't even know what kind of figure is it. Okay, I'm sorry. Okay, finally, doing the example 7.23. Okay, you will see this is almost the same examples, but you don't know any numbers here. You just know that this is it looks like a midpoint theorem as we learned before. And then we can see this is two triangle. Actually, they're the similar case. So ADE and then the ABC, they're similar triangle, right? We don't know all the numbers, but we know the ratio. We can see that if AD is 1, then AB should be 2, right? Because this is in a double, 1 to 2. Therefore, if we want to find the area of ADE, right? So we can see the bigger triangle is ABC. So we're using the same thing as it before, L1 to L2. Okay, although we don't know the exact numbers of L1 and L2, but we know the ratio of L1 to L2 should be 1/2. So 1/2 with a square for the right hand side. And then because we know the bigger area of the triangle should be 40. So A1 we don't know yet. So we multiply 40 to the right hand side. So we know that A1 should be 10 cm square. Okay, and then actually you will see that if the bigger triangle should be 40 and then smaller one should be 10, so what is this quadrilateral should be? And then it's 40 minus 10, it should be 30 cm square. Then we are done for this. Okay, so I would like to say for example 7.23, they are also using the formula directly, but without the exact number. Actually, you just need to know is the ratio, because as we said it before, the ratio of the length square is the area ratio. So you just need to know is the ratio of the length for this case. Okay, therefore, after the 7.6a, I would like to say that if the similar figures, the length ratio square is the area ratio. That's all we need to know for this. Okay, so for 7.6b, and then this is almost the same, but this case now becomes the similar solid, not the 2D things. It's now become 3D, but the things is almost the same. If we got a similar solid, for example, for the cubes, then their length in the ratio of k, then what is their volume? The volume ratio should be in the power of 3. Okay, for example, if this is a ka square, this should be, okay, I do it step by step. This side to this side is the ratio of k to 1, right? Because the above is ka, then the bottom one is a, then we just cancel it out, is k to 1. If the area, it should be ka times ka for the base area for this part. Then for the bottom is a square. Then you will see this is a k square over 1. Okay, you will see this is come up again. The area is the length ratio square, right? Okay, for the volume, how can we calculate the total volume? The ka to the power of 3. Okay, and then a should be power of 3, because a times a times a is the volume of the cube. Then you will see now this should be k cube over 1, and then you will get this. If this is a similar figure in 2-dimension case, then we just have to calculating the area. So the length square is the area. Okay, then if we have a similar solid in 3D case, therefore the ratio of the length in the power of 3, it should be equals to the volume. Okay, therefore we can see the examples directly. Again, you will see that this is a similar pyramid. Okay, but you don't even know what kind of pyramid he doesn't draw for you, and then we just need to know is the ratio of the length, and then we can calculate, come up the volume or the areas. Okay, now you can see this time we are talking about the areas of the pyramid. Therefore, we don't need to using the volume formula. We just need to using the area formula. So for the area formula, and then we just need to write down is the same to we have learned it before, because no matter this is a similar solid or a similar figure, if they are similar, then their length ratio square will equals to the area ratio, no matter this is the one side of the surface area or the total surface area, they will all be the same. Okay, therefore we can see this, the length ratio should be 3 over 7, so we have a square here, and then the A1 is the smaller area because we have the corresponding to the length, and then the bigger area should be 98. So we apply this formula directly. We multiply the 98 to the right hand side, we will get 18 cm square. Okay. Okay, therefore, for the example 7.25, you will see that we got the volume case now. We got two similar clone, no matter what kind of figure it is. So they are similar for the 3D solid. Okay, now we can see the volume is 1 over 8 to the larger cone. And then they told us to find the ratio of the height. Okay, ratio of the heights, no matter this is a height or this is a side, if they are similar figure, they will have a similar ratio here. Therefore, we just need to apply the formula directly again, but this time it's the volume ratio, so L1 to L2 with the power of 3 times if this is volume. Okay, so we just apply directly. V1 is a smaller one, so 1/8. V2 is the bigger one, 8. Okay, so this is L1 to L2 because I want to find the volumes now. So we just keep L1 to L2 here, it's okay. And then we just make a cube root of 1/8. Then we'll have single L1/L2. After using the calculator, we know that L1/L2 it should be 1/2. Therefore, I find out the ratio of the height. It should be also in the ratio of 1/2. Again, I would like to mention that no matter this is a height or we call it is a one kind of side, they all have the same ratio. Okay, so if the total surface area for the larger clone is 100, find the total surface area for the smaller clone. Okay, again, because we got the length ratio now, L1 to L2 is 1/2, right? And then we just apply the A1/A2 equals to the ratio of the length square. So A1 to A2, because we already have the larger area for 100, it should be equal to 1/4 because L1/L2 is square, and then it changed to 1/4, and then we multiply 100 to the right hand side, we have 25 cm square. Okay, so you will see this is not quite difficult, but actually you will see that this is just, you know that similar figure for area is a square of the ratio of the length. If we need to calculate the volume, we need to have a cube of ratio of the length. Okay, so finally, so already this is a bit long, but I need to finish this example. So you can see this is a similar solid here, because you will see that this kind of clone on the smaller part is totally in the right proportion to the larger clone. So there's similar clone here. Okay, so need to find out the ratio of the curved surface area. As we mentioned, the first thing, if we want to find the ratio of the area, we need to have a square of the length. So the first thing we need to find out is the length ratio. So you can see the smaller one we have a 4. For the bigger clone, we have 4 plus 6. It is 10 for the length. So if we get the length ratio, it should be 4/10 with a square. So you can see that 2/5 with a square, it is 4/25. And then actually you just apply this formula directly, and then you will have the ratio of 4/25. Okay. Second things, you find the volume of the clone VAB to the frustum ABDC. Okay, so first we find the volume of the bigger clone to the smaller clone. So we need to find out V1 to V2 first. Remember, this is the L1 to L2 with a clip. Therefore, what we need to do is, because the length ratio we have calculated it before is 4/10 with a clip equals to V1 to V2, okay? And then you will see that V1 to V2 is equals to 8/125 after using the calculator. That means you will see that the larger part of the cone, the bigger cone, 125. The smaller cone is 8. Okay, so if we want to find the clone VAB, we know already it should be 8. But for the frustum or ABDC, it should be 125, the bigger volume minus the smaller volume minus 8. It should be 113. Okay. And then you will see that sorry, 117. It should be 117. So you will see that this should be 8 to 117. That's how it goes actually. So the volume ratio should be 8 to 117. Okay, therefore, again, the formula you need to know is the similar figures L1 to L2. If this is a square, this is the area ratio. If the length ratio in the cube, it should be volume ratio. So let's try in this case for the similar figures. So let's finish all the quick practice and also all the consolidation corner, and that's all for this chapters.